Taub knew his finding had major implications. If the monkeys could move their deafferented arms without having feeling or sensation in them, then Sherrington's theory and Taub's teachers were wrong. There must be independent motor programs in the brain that could initiate voluntary movement. Behaviorism and neuroscience had been going down a blind alley for 70 years. Taub also thought his finding might have implications for stroke recovery because the monkeys, like stroke patients, had seemed utterly unable to move their arms. Perhaps some stroke patients, like the monkeys, might also move their limbs if forced to. Taub was soon to find that not all scientists were as gracious about having their theories disproved as Keller was. Devout followers of Sherrington began finding fault with the experiment, its methodology, and Taub's interpretation. Granting agencies argued about whether the young graduate student should be allowed further money. Taub's professor at Columbia, Nat Schoenfield, had built a well-known behaviorist theory on the basis of Sherrington's deafferentation experiments. When it came time for Taub to defend his PhD, the hall, usually empty, was packed. Keller, Taub's mentor, was away, and Schoenfield was present. Taub presented his data and his interpretation of it. Schoenfield argued against him and walked out. Then came the final exam. Taub, by this time, had more grants than many of the teaching faculty and chose to work on 2 major grant applications during the week of the final, expecting to make it later. When he was denied a makeup and failed for his insolence, he decided to complete his PhD at New York University. Most scientists in his field refused to believe his findings. He was attacked at scientific meetings and received no scientific recognition or awards. Yet at NYU, Taub was happy. I was in heaven. I was doing research. There was nothing more that I wanted. Taub was pioneering a new kind of neuroscience that merged the best of behaviorism, cleansed of some of its more doctrinaire ideas, and brain science. In fact, it was a fusion anticipated by Ivan Pavlov, the founder of behaviorism, who, though it is not widely known, had attempted in his later years to integrate his findings with brain science and even argued that the brain is plastic. Ironically, behaviorism had in one way prepared Taub to make important plastic discoveries. Because behaviorists were so uninterested in the structure of the brain, they had not concluded, as had most neuroscientists, that the brain lacked plasticity. Many believed they could train an animal to do almost anything, and though they didn't speak of neuroplasticity, they believed in behavioral plasticity. Open to this idea of plasticity, Taub forged ahead with deafferentation. He reasoned that if both arms were deafferented, a monkey should soon be able to move them both because it would have to do so to survive. So he differentiated both limbs, and in fact the monkeys did move both. This finding was paradoxical. If one arm was differentiated, the monkey couldn't use it. If both arms were deafferented, the monkey could use both. Then Taub deafferented the whole spinal cord so that there wasn't a single spinal reflex left in the body, and the monkey could not receive sensory input from any of its limbs. Still, it used its limbs. Sherrington's reflexological theory was dead. Then Taub had another epiphany, the one that would transform the treatment of strokes. He proposed that the reason a monkey didn't use its arm after a single limb was deafferented was because it had learned not to use it in the period right after the operation when the spinal cord was still in spinal shock from surgery. Spinal shock can last from 2 to 6 months, a period when the neurons have difficulty firing. An animal in spinal shock will try to move its affected arm and fail many times during those months. Without positive reinforcement, the animal gives up and instead uses its good arm to feed itself, getting positive reinforcement each time it succeeds. And thus the motor map for the deafferented arm, which includes programs for common arm movements, begins to weaken and atrophy. According to the plasticity principle of use it or lose it, Taub called this phenomenon learned non-use. He reasoned that monkeys that had both arms deafferented were able to use them because they never had the opportunity to learn that they didn't work well. They had to use them to survive. But Taub thought he still had only indirect evidence for his theory of learned non-use. So in a series of ingenious experiments, he tried to prevent monkeys from learning non-use. In one, he deafferented a monkey's arm. Then, instead of putting a sling in the good arm to restrain it, he put it on the deafferented arm. That way, the monkey would not be able to learn that it was of no use in the period of spinal shock. And indeed, when he removed the restraint at 3 months, long after the shock had worn off, the monkey was soon able to use the deafferented limb. Taub next began investigating what success he could have teaching animals to overcome learned non-use. He then tested whether he could correct learned non-use several years after it had developed. By forcing a monkey to use the deafferented arm, it worked and led to improvements that lasted the rest of the monkey's life. Taub now had an animal model that both mimicked the effects of strokes when nerve signals are interrupted and limbs cannot be moved, and a possible way of overcoming the problem. Taub believed that discoveries meant that people who had had strokes or other kinds of brain damage, even years earlier, might be suffering from learned non-use. He knew the brains of some stroke patients with minimal damage went into an equivalent of spinal shock, cortical shock, which can last for several months. During this period, each attempt to move the hand is met with failure, possibly leading to learned non-use. Stroke patients with extensive brain damage in the motor area fail to improve for a long period, and when they do, only recover partially. Taub reasoned that any treatment for stroke would have to address both massive brain damage and learned non-use, because learned non-use might be masking a patient's ability to recover. Only by overcoming learned non-use first could one truly gauge a patient's prospects. Taub believed that even after a stroke, there was a good chance that motor programs for movement were present in the nervous system. Thus, the way to unmask motor capacity was to do to human beings what he did to the monkeys, constrain the use of the good limb and force the affected one to begin moving. In his earlier work with monkeys, Taub had learned an important lesson. If he simply offered them a reward for using their bad arms to reach for food, if he tried to do what behaviorists called conditioning, the monkeys made no progress. He turned to another technique called shaping, which molds a behavior in very small steps. So a deafferented animal would get a reward not only for successfully reaching for the food, but for making the first, most modest gesture toward it. In May 1981, Taub was 49, heading up his own lab, the Behavioral Biology Center in Silver Spring, Maryland, with grand plans to transform the work he was doing with monkeys into a treatment for stroke. When Alex Pacheco, a 22-year-old political science student at George Washington University in Washington, D.C., volunteered to work in his lab.